Hey guys, today we'll talk about rotational motion and angular momentum. And the topic for this lesson will be rotational motion. First and foremost, let's recall what is kinetic energy. If I were to ask around the room, what do you remember about kinetic energy? I think most students will say that kinetic energy is the energy of motion. And then hopefully you'll remember the formula for it, which is 1/2 times mass times velocity squared. I want to recall how to find velocity. Velocity will be displacement divided by time. I know I should say change in time, but let's just generalize this to displacement divided by time, okay? So now I want you to look at this rotating lever. And then I want you to ask the person next to you if you believe this lever has kinetic energy. Okay, look at it closely. Now let's see how to answer this question. Think about the displacement of the lever, okay? Not how many degrees, what is the rate at which it's completing a full rotation. I want you to think about the displacement, linear displacement. Well, in this case, it's not moving anywhere, so the linear displacement would be 0 meters. If the linear displacement is 0 meters, then the velocity would be 0 divided by time, which is 0 meters per second. If there's 0 velocity, there's no motion. Therefore, the kinetic energy should be 0 joules. You might be confused because you can say, well, this is rotating. How is it that it doesn't have any kinetic energy? Now, we have reached that point in physics where we have to define what type of kinetic energy. Not only what type of energy, but what type of kinetic energy. Because although this is not moving linearly, this is rotating, okay? So this 0 is correct, but only for translational motion. What that means is that the rotating lever, has rotational motion, which is, in this case, rotational kinetic energy. Let's highlight rotational kinetic energy. Before we compare those two energies, rotational and translational kinetic energy, let's go back to inertia. Because in order to define rotational kinetic energy, we need to define moment of inertia. Let's start with inertia. We learned this like in October. So inertia is related to Newton's first law of motion. And then in class, we defined inertia as follows. We said that inertia was the tendency of an object to keep its state of motion. So if the object is moving, it wants to keep moving in a straight line. And if the object is at rest, it wants to remain at rest. Okay? And then we connected this concept of inertia with mass. We said that mass is the quantitative measurement of inertia. Think about it this way. If you had a sedan, let's say Honda Civic, in a dually F450, those trucks that have 4 wheels in the back, which one is harder to push? Obviously the truck. Well, which one has more mass? The truck, which means it has more inertia. So we connect inertia with mass. The more mass something has, the more inertia it'll have. Likewise, if you're trying to stop that truck, it'll be very hard. Whereas a Honda Civic, well, I mean, I don't know if you can stop it, right? But something can stop it more easily than the truck. So don't forget, inertia and mass are related. The more you have of one, the more you'll have of the other. You can think of inertia as the resistance to change its state of motion, okay? Resistance is a good word. Now, I have a picture of two eggs, one hard-boiled, one raw. How can you know which one's which? Some of you might say, well, I'll just shake them to see which one is which. But let's say you couldn't do that. Let's say you cannot get him off the table. You can just touch him for a few seconds. And of course, you don't break him, because then it stinks. What can you do? Pause the video, discuss with your partner. How can you know which one's which? I said pause the video. All right. Some of you might say you spin it. But the question is, why do you spin it? And in class, I had a student who said, well, I think if you spin both of them, one of them will have a more tight rotation and the other one might be a little wobbly. And here's a video of what happens. Pay attention. As you can see, one does spin in a more uniform fashion, the other one gets wobbly. Furthermore, when I stop both of them, one actually stops and the other one does not. Which one's which? I'm hoping you saw that, or you said that. The raw one is the one that keeps spinning because of the yolk. And that's correct. What we're doing is we're stopping the shell, but not the yolk. It has inertia still. Because of that inertia, it wants to keep moving, it wants to keep rotating. Not any type of inertia, but in this case, it'll be the rotational inertia, okay? So let's write this down. So the raw egg has more rotational inertia, thus it is harder to make it spin, and once it is spinning, it doesn't want to stop. Just like traditional inertia, the more you have of it, the more resistance you have to a change of motion. And rotational inertia is a good word or a good expression, but the actual physics definition for that is moment of inertia, okay? Moment of inertia is analogous to mass. Sorry, not to mass, to regular inertia. Just like angular velocity is analogous to linear velocity, well, moment of inertia is analogous to inertia. So we'll write the definition for inertia based on what we wrote down for this traditional inertia. But instead of state of motion, we'll replace that with rotation, okay? So let's define moment of inertia. The tendency of an object to keep its state of rotation. That means if an object is rotating, it wants to keep rotating. If an object is not rotating, it wants to remain that way. We can say that moment of inertia is resistance to rotation or to stop rotating. If we go back to the two eggs, the hard-boiled one has less moment of inertia because it was easier to get it to spin, and when I try to stop it, well, it was fairly easy. Whereas the raw egg has more moment of inertia because it was harder to get it to spin, and once it was spinning and I tried to stop it, it didn't want to stop. So the hard-boiled egg has more or higher the raw egg has higher moment of inertia. Okay, now we can go back to rotational kinetic energy. To do this, let's think about the formula for kinetic energy, the regular kinetic energy, okay? So we know that kinetic energy is 1/2 mv squared. But we said that in this case, we can no longer say just kinetic energy, so we'll fix this one a little bit. This means translational kinetic energy. Let's define rotational kinetic energy. The formula keeps the 1/2. The analogous quantity for mass, well, mass was related to inertia, and the analogous of inertia was moment of inertia. So we can say that the analogous quantity for mass when you have rotation is moment of inertia. And we define this with letter I. Okay? And the analogous quantity for velocity when you have rotation is angular velocity omega. 1/2 I omega squared. This is rotational kinetic energy. Another way to think about moment of inertia is rotational mass. Okay? It's not, most books won't have that, but I think it's a good way to remember that the analogous quantity for mass is rotational mass, which happens to be moment of inertia. Okay? I'm not going to derive the formula and tell you where it comes from. I'm just going to give you the moment of inertia quantity. So we define that with an I. This is of a point mass. Okay? It'll be mass times radius squared. Let's see what that means. So I is moment of inertia, m is mass, and r squared is the distance to the center of rotation to the axis of rotation. So in this case, moment of inertia is affected by mass and distance. I want you to think about which one would have more impact, changing the mass or changing the distance. Well, in this case, it'll be the distance because of the squared. When you change the distance from the axis of rotation of an object, and then I'll show you in class how you can do that. That would have more impact. So if you double the distance, you would quadruple the moment of inertia. Whereas if you double the mass, you would just double the moment of inertia. Okay? So distance has a greater impact when talking about moment of inertia. Now, pause the video so you can get your hand out. And then I want you to read question 1. It says, for the items above, assume that m, mass, and r, distance to the axis of rotation, remain constant. Rank the items in terms of moments of inertia from least to greatest. Okay? Pause the video and check the answer with me.